Okay, in this lecture we're going to continue with our section 4.1 material on functions of two or more variables. So in the first part of this lecture we had considered functions of two variables and we saw how to evaluate a function of two variables at a point, or how to determine its domain or range. We saw some examples where we could visualize the domain as some subset of the xy plane. So in the second part of this lecture, we'll consider the graph of a function of two variables, and then we'll briefly introduce functions of three variables and extend some of the concepts that we've talked about in the first part of this section to functions of three or more variables. So let's start by defining the graph of a function of two variables. So here, suppose that f is a function of two variables, say x and y, whose domain is a set D. Then we would define the graph of this function f as the set of all points x, y, z in 3 space, such that z, that is the z coordinate of that point, is the value of the function f at xy, where xy is a point within the domain of our function. So what we're describing here is a set of points in space. So we're looking at a surface. The graph of a function of two variables would be a surface in 3 space. So here, the graph of our function f of two variables is a surface defined by the equation z equals f of xy. So our z coordinate for any point on the graph must be the value of the function f at a point xy in the domain. So we can visualize the graph of this function as lying directly above or below the domain D in the xy plane. So as a visualization here, suppose that we have some function and we have found its domain in the xy plane as D, so we have some region in the xy plane. And for points that we choose within our domain, let's say some point xy, we can find the value of the function f at this point xy, and that tells us how far that we would move upward or downward from that point to get a point on our surface. So we would find the corresponding point in space, x, y, f of xy, and by choosing several different points in our domain and finding the corresponding values for these points, we trace out a surface, which we'll label as S, in 3 space. Now the graph that I've shown here has a surface which lies above the xy plane, so all of my functional values would be positive here. Now if we had some values of our function that would be negative, then our surface might cross below the xy plane if we have, say, a negative z value. So now that we've defined the graph of a function of two variables as a surface, let's look at some examples where we're given a function of two variables and we're asked to describe its graph. So if we have the function in part A, f of xy is equal to 3, to consider the graph of this function, we're looking at the set of all points such that z is equal to f of xy, which was defined as 3. So we're looking at the surface defined by z equals 3, which is a plane that lies 3 units above the xy plane. It has a constant z value. So we could try to visualize this here. If we have in space our x, y, and z axes, we would be talking about the plane defined by z equals 3. So that is the plane parallel to the xy plane and passing through z equals 3. So we would have this plane that lies 3 units above our xy plane. So to indicate that it's passing through 3, we might add one line here. So this would be our surface S. Now in part B, we have the function f of xy is 4 minus 2x minus y. So the graph of this function would be the set of points in space such that z is equal to the value of our function, 4 minus 2x minus y. Now, if we rewrite this equation a bit, if I move all of my variables to, say, the left-hand side, I would have the equation of my surface as 2x plus y plus z is equal to 4. And we recognize this equation as being in the standard form of the equation of a plane. So we have a plane in space, and to visualize what our plane looks like, we could find its x, y, and z intercepts. So here, let's sketch the first octant in x, y, z space. Now, the x-intercept of this plane is found by setting y and z equal to 0. So it follows that x would be equal to 2. Our y-intercept is found by setting x and z equal to 0 in the equation. So we would have y as 4. And our z-intercept would be 4. So we're looking at the plane in space, shown here. Of course, this extends infinitely in all directions, but we get what the part of our plane looks like in the first octant. Now in part C, we have the function f of xy is x squared plus 9y squared. So the graph of this function would be the surface defined by setting z equal to f of xy. That is, z equals x squared plus 9y squared. And we can recognize this equation immediately as the equation of a quadric surface. This is the elliptic paraboloid opening upward along the z-axis. So to try to visualize our surface here, let's sketch what this would look like. So we have our x, y, z axes, and this is the equation of an elliptic paraboloid. So our cross sections or our traces in planes parallel to the xy plane would be found by taking fixed values of z, and we would have something of the form x squared plus 9y squared is equal to a constant. So that would define an ellipse that's extending a little further in the y direction. So we would have these ellipses that become larger as z is becoming larger. And we have this sort of paraboloid here. So this would be a rough sketch for our surface. And of course, it extends infinitely far upward as we keep moving along the z-axis. So here in this problem, we were asked to describe the graphs of our surfaces. We've sketched them here. To give our description in part A, we could say that we have a plane. In part B, we have, again, a plane. And then in part C, we had an elliptic paraboloid. Centered about the z-axis. Now, in general, if we're trying to sketch the graph or visualize the surface, which would be the graph of a function of two variables, well, we might not always have a function that's as simple as what we considered in our previous examples, where the equation of our surface is a surface that's familiar to us. We might have some more complicated surfaces. But to get some idea of what a more complex surface, or what the graph of a more complicated function of two variables would look like, we can consider something called level curves or traces of our function. So let's define what we mean by level curves. We would say that the level curves of a function of two variables are the curves defined by setting the function f of xy equal to k, where k is some constant that lies in the range of our function. So we're looking at specific fixed values of z and setting our function equal to that specific z value. So what we're doing geometrically are looking at curves in planes parallel to the xy plane. So these level curves are actually the horizontal traces of the graph of the function f in the plane z equals to k. Now a graph of all of the level curves is what is called a contour plot. So here we have an illustration of this. Let's say that we have some surface S, which is the graph of a function of two variables, x and y. And by choosing specific values of z, or by considering slicing our surface with horizontal planes at different levels, we're tracing out these level curves. So here, by looking at the intersection of our surface with these different planes defined by different values of z, we get curves, and if we project these curves down onto the xy plane, we have a contour plot. So the projection of all of these level curves onto our xy plane gives us a contour plot. And these contour plots are used frequently in topographic maps. They give us a way to visualize a three-dimensional surface in 2 dimensions. Say in map making, we can determine by looking at how closely these level curves are together, that would indicate that we have a surface that is a little more steep at some point. So let's consider an example working with these level curves or contour plots, make these concepts a little more familiar. So here we are asked to sketch the level curves for each function corresponding to the given values of k. So in part A, we have the function f of xy is equal to x squared plus 4y squared. And we're asked to sketch the level curves corresponding to these values, k equals 0, 4, and 16. So in general, our level curves are defined by taking the function f of xy, which is x squared plus 4y squared, and setting it equal to k. So generally speaking, we're going to have ellipses for our level curves. We recognize this equation as representing an ellipse in the xy plane. So to sketch the specific level curves that we're asked for, we would substitute in the indicated values of k. So starting with the value k equals to 0, we would have x squared plus 4y squared is 0. So we would have an ellipse of radius 0. That is just a single point at the origin. So let's keep track of our level curves by sketching them over here. So for our first level curve corresponding to k equals 0, we have a single point. Now for the next value of k that we're given, that is if k is equal to 4, we would have x squared plus 4y squared equals 4, which again represents an ellipse. To sketch this, we could find our x and y intercepts. So our x-intercepts would be at plus or minus 2, and our y-intercepts at plus or minus 1. So we would have the ellipse shown here. This would be our level curve for k equals 4. So that is, if we were to move upward from the xy plane 4 units, we would see this curve as the intersection of our surface with this plane. And for our last value that we were given for k equals to 16, we have the curve x squared plus 4y squared is equal to 16. So this would be the ellipse whose x-intercepts are at positive and negative 4. And whose y-intercepts would be given by plus or minus 2. So we would have the ellipse shown here for k equals to 16. So we see that as we're moving upward from the xy plane, that is, the larger we choose the value of k, or if we're looking at planes moving further and further upward from the xy plane, we get ellipses of a larger area. So our surface, we can visualize from that, and for this particular example, actually, we know what our equation for the surface looks like. If z is x squared plus 4y squared, well, this is an elliptic paraboloid. So this is, of course, what we would expect for our level curves to look like. As we're moving upward from the xy plane, we're slicing our surface, and we're getting ellipses of larger area. Now, let's consider another example. In part B, we have f of xy is y minus x squared, and we're asked to sketch our level curves for these indicated values of k. So again, we would define the level curves by setting our function equal to some fixed constant k, and we would see here, solving this equation, y would equal x squared plus k. So in general, our level curves are going to be parabolas, where the value of k would affect the vertex of our parabola. So if we are sketching the level curves for specific values, well, if k is equal to -1, we have the equation y equals x squared minus 1. So let's sketch this. In our xy plane, this would be the parabola opening upward, whose vertex is at 0, -1. If k is equal to 0, we have y equals x squared, which would be the parabola whose vertex is at the origin. And then similarly, if k is equal to 1, we have x squared plus 1, so the parabola whose vertex would be at 0, 1. And if k is equal to 2, we would have the parabola x squared plus 2, whose vertex would be at 0, 2. So sketching these other level curves, we have the parabola opening upward, whose vertex is at the origin, or whose vertex is at the point 1, if k is +1, or the parabola whose vertex is at 2 if k was equal to 2. In general, we have a parabola whose vertex is at the given value of k. So this gives us a visualization of what our surface looks like. Here we have cross sections that are these parabolas. So we have a sort of parabolic cylinder, but kind of on a slant here. The larger that we take the value for k, the larger our vertex becomes. So in 3 dimensions, let's see if we could get a rough sketch for this. We would have our level curves as these parabolas whose vertex is moving upward in the y direction as we are increasing the value of z. So we have a sort of parabolic cylinder shape, but where this appears to be like on an angle, a slanted parabolic cylinder for our surface. Now, in part C, we have the function f of xy defined as the square root of 4 minus x squared minus y squared. We're asked to sketch our graph here for the indicated values of k. So we're going to let our function f of xy, which is the square root of 4 minus x squared minus y squared equal k. And simplifying our equation a little bit, well, if we square both sides, we have 4 minus x squared minus y squared is k squared, or 4 minus k squared is equal to x squared plus y squared. So if we have the sum of x and y squared is equal to some constant, our level curves would be describing circles in general, where the value of k affects the radius of our circle. So looking at the specific values of k that we were given here, well, if k is equal to 0, our equation is x squared plus y squared equals 4. So we would have a circle centered at the origin of radius 2. This would be our level curve for k equals 0. Now if k was equal to 1, we would have x squared plus y squared is equal to 3. So again, a circle centered at the origin now of radius square root 3. And if k is equal to 2, then we have x squared plus y squared is equal to 0. So that would be a circle of 0 radius, or just the single point consisting of the origin, if k is 2. So for our surface, as we're moving upward from the xy plane, that is, the larger we're taking the value of k, we're getting circles of a smaller radius. So here we're actually looking at part of a cone that is below the plane z equals 2. So in 3 space, we would have something that looks like the following. Our trace in the plane z equals 2 was a single point, xy equals 0, so we have 0, 0, 2 in space. In the plane that was 1 unit above the xy plane, we had a circle of radius root 3. And in the plane where k equals 0, that is the xy plane, we had a circle of radius 2. And of course, the smaller that we would make the value of k, or the larger that we would have the magnitude of k, we would be getting circles of larger radius. But here, looking back at our restriction for the surface, k was defined as the positive square root, so we're only considering points above the xy plane, since k has to be positive here. So we're looking at this portion of a cone that lies above the xy plane. So you get a little visualization of our surface here. Now the last thing that we'll take a look at in this section is extending some of the concepts that we've described to functions of 3 or more variables. So here we'll define formally a function of 3 variables, and of course functions of more than 3 variables would be defined similarly. But we would say that a function of 3 variables is a rule that assigns a unique real number, denoted as f of xyz, to each ordered triple xyz in subset D, which is a subset of space. And the level curves of, the level surfaces of a function of 3 variables are these surfaces defined by f of xyz equals to k, where k is some constant. So just like we had defined level curves of a function of 2 variables as the curves defined by setting our function equal to some constant, we can define level surfaces of a function of 3 variables as the surfaces in space defined by setting our function equal to some constant. So in our last example, we are asked to find the domain of the given function of 3 variables and describe its level surfaces. So in part A, we have the function f of xyz, defined as the square root of some polynomial of 3 variables. And in order for this function to be defined as a real number, we need the expression under the radical to be non-negative. Now, solving this inequality, we have 16 has to be greater than or equal to 4x squared plus 4y squared plus z squared. So we could say the domain is the set D of points in space of the form xyz such that this inequality holds. 4x squared plus 4y squared plus z squared has to be less than or equal to 16. Now geometrically, we can think about what this domain looks like in space. We recognize the equation 4x squared plus 4y squared plus z squared as equal to 16 as representing an ellipsoid in space. So here a rough sketch for our domain. We would have the ellipsoid whose x-intercepts would be positive or negative 2, whose y-intercepts would be positive and negative 2, and whose z-intercepts are positive or negative 4. So our domain would be this ellipsoid shown here, the interior of this ellipsoid, since the sum of the square values had to be less than or equal to 16. Now we were also asked to describe the level surfaces of this function. So the level surfaces, again, are defined by taking the function and setting it equal to some constant k. So simplifying this equation, if we square both sides, we would have 16 minus 4x squared minus 4y squared minus z squared is equal to k squared. Or rearranging the equation, 16 minus k squared is equal to 4x squared plus 4y squared plus z squared. So this equation would represent an ellipsoid where the value of k would affect what our x, y, or z intercepts are. But generally speaking, our level curves would be ellipsoids here, or our level surfaces are ellipsoids. Now for part B, to determine the domain of this function, which is the natural log of some polynomial of 3 variables, we need the argument of this logarithm, x minus z minus x minus 2y, to be strictly greater than 0. And rearranging this equation a little bit, we could maybe rewrite this as z has to be greater than x plus 2y, which represents the region above some plane in space. So here we can say the domain is the set D of points in space x, y, z, such that this inequality holds. Z has to be greater than x plus 2y. So we're talking about some region in space that lies above a plane. Now, to describe the level curves of this surface, or the level surfaces of this function, we would take the function, natural log of z minus x minus 2y, and set it equal to some constant k. So simplifying a little, we have z minus x minus 2y would be e to the k, or z would be equal to, well, let's maybe rewrite it in this way. It'll make describing our surfaces a little easier. I could say negative x minus 2y plus z is e to the k, where k is some constant. So this sort of equation represents a plane in space where the value of k would just affect our x, y, and z intercepts of these planes.